Take a raw, isolated piece of crystalline silicon. In its pure state, it's essentially a rock, a poor conductor with a highly stable atomic lattice. The engineering challenge of modern electronics is taking that inert material and forcing it to act as a precisely controlled valve for electrical current. By introducing specific chemical impurities, a process called doping, we alter that lattice to create distinct p-type and n-type semiconductor regions. When we join 3 of these distinct regions together, we create a bipolar junction transistor. This 3-terminal active device can instantly switch between acting as an insulator or a conductor, based entirely on a small applied signal voltage. Every bipolar transistor is divided into 3 functional zones: the emitter, the base, and the collector. Depending on how we sandwich those layers together, we get 2 distinct construction methods. We can place an n-type semiconductor between 2 p-types to create a PNP transistor, or place a p-type between 2 n-types to create an NPN transistor. Physically, the junctions between these materials behave exactly like 2 back-to-back diodes. To keep the electrical routing clear in schematics, the circuit symbol for both types features an arrow on the emitter terminal. That arrow always points in the direction of conventional current flow, dictating the necessary polarity of the power supply. Regardless of the configuration, the macroscopic behavior of the entire system is governed by a strict mathematical rule. The total current flowing through the emitter is exactly equal to the sum of the collector current and the base current. Because of the physical widths and doping concentrations of these 3 layers, a microscopic current injected into the base controls a massive current flowing through the collector. In physical terms, the transistor functions as a current-controlled current valve. Knowing that the base acts as a valve is useful conceptually, but to actually design a circuit, engineers have to translate that physical behavior into predictable mathematical curves. We do this using current voltage or IV curves. At the input, the base emitter junction behaves predictably. Just like a standard forward bias diode, it refuses to conduct until the voltage reaches a strict threshold, the knee voltage, which is roughly 0.7 volts for silicon. Once crossed, the base current begins to flow. This graph plots the collector-emitter voltage against the resulting emitter current. It provides the specific data needed to identify the component's operational boundaries under different loads. Most analog engineering takes place in the active region. This is the broad, flat plateau spanning the center of the graph, where the lines representing fixed base currents are parallel and evenly spaced. Here, the transistor acts as a linear, proportional amplifier. To the extreme left lies the saturation region. This steep left edge represents a state where the transistor is fully conducting, allowing maximum current to flow, while the voltage drop across the component hits its minimum level. At the absolute bottom edge of the graph is the cutoff region. Here, base current drops to 0. The depletion regions inside the silicon expand, and the transistor ceases to conduct entirely, acting as an open circuit. By mapping these regions, we derive 2 critical mathematical ratios. The first is alpha, the ratio of collector current to emitter current. Because a small amount of current is always required to bias the base terminal, alpha is always slightly less than unity, typically around 0.98. The more critical metric is beta, or HFE. This is the current amplification factor, the ratio of the massive collector current to the tiny base current. If a transistor has a beta of 100, a 1 milliamp signal at the base yields a 100 milliamp flow at the collector. This is the true measure of the device's gain. These curves and ratios establish the rigid mathematical boundaries of the transistor. An engineer must design the surrounding circuit to force the component to operate strictly within the desired region to maintain stability. A transistor sitting on a desk has potential gain, but its actual function is dictated entirely by its topology. How it amplifies a signal depends completely on which of its 3 terminals is tied to the common ground reference. In the common base configuration, the base is tied to ground. This geometry yields a high voltage gain, but because the input current is the total emitter current and the output is the slightly smaller collector current, its current gain, the alpha we defined earlier, is less than 1. The input signal is driven between the emitter and the base, and the output is extracted across the collector and the base. Rotate the configuration to a common collector and the profile inverts. This setup, often called an emitter follower, yields high current gain but 0 voltage gain. Because the input signal is applied to the base while the output follows the emitter, the input circuit only draws the very small base current, creating high input impedance. Conversely, the output is driven by the full emitter current, resulting in low output impedance. This makes the topology ideal for impedance matching, acting as a buffer between high resistance sources and low resistance loads. By rotating the physical orientation of the semiconductor relative to the circuit's ground, we selectively harvest either voltage gain, current gain, or impedance buffering. The most widely implemented topology is the common emitter configuration. It is a versatile choice because it is the only arrangement that provides both high current gain and high voltage gain simultaneously. Here, the input signal is fed into the base, and the amplified output is taken from the collector. The emitter terminal acts as the shared common connection point for both the input and output stages. This creates a direct causal chain. As input voltage increases, base current increases, forcing a drastically larger collector current. As collector current surges through the load, the collector voltage is pulled down. This results in an amplified output exactly 180 degrees out of phase. While it inverts the signal, the simultaneous multiplication of current and voltage creates exceptional power gain. This efficiency makes the common emitter the primary choice for general-purpose signal amplification. Mathematical gain is irrelevant if the physical material fails. A theoretically correct common emitter amplifier will break down immediately if the design violates the hardware constraints of the silicon. These constraints are hard-coded into the manufacturer's datasheet. Designers must verify maximum power dissipation, absolute maximum collector current, and the reverse breakdown voltages before permanent damage occurs. Allowable power dissipation is tied to the package's physical footprint. A tiny plastic TO92 is limited to small signal amplification. To drive power and reject heat, engineers switch to a large metal TO3 package, using the casing as a heatsink to dissipate thermal energy. Every electronic design is a compromise between the mathematical requirement for gain and the thermodynamic limits of the physical materials. If we connect a raw AC audio signal directly into the base of an amplifier, we hit an inherent physical constraint. AC signals alternate between positive and negative voltage, but a negative swing will reverse bias the base emitter junction, forcing the transistor to shut off and destroying half the waveform. To solve this, engineers use transistor biasing. This is the process of setting a steady-state DC operating voltage at the base, effectively lifting the entire AC signal so that even its lowest negative swing remains above the transistor's shutoff threshold. We establish this baseline by picking a specific target on the transistor's characteristic curve, called the Q point, or quiescent operating point. This is the exact state the transistor idles in before any AC signal is introduced. This diagram illustrates incorrect calibration. If the resistor set the Q point too high, the input pushes the transistor into saturation, and the top of the wave is clipped flat. Conversely, if set too low, the swing drags the transistor into cutoff, clipping the biome half. Without calibrating the supply voltages and resistor values to lock in a central Q point, faithful signal reproduction is not possible. The simplest way to set that Q point is base bias, which uses a single resistor to drop voltage from the main supply and bleed a steady current directly into the base terminal. But base bias is vulnerable. The beta value of a transistor shifts as the component heats up, and manufacturing tolerances mean no two transistors share the exact same beta out of the box. With a single resistor, these variations cause the Q point to drift, resulting in unpredictable performance. To solve this drift, the standard engineering approach is voltage divider biasing. Instead of a single resistor, two resistors form a potential divider across the supply line, feeding the base terminal from the center node. This resistor divider clamps the base voltage to a specific ratio of the supply voltage. By making this node's voltage dependent on external resistors rather than internal current, the Q point remains stable, even if the transistor's inherent beta fluctuates due to temperature or manufacturing variance. Robust circuit design is about forcing the system to remain stable, despite the inevitable imperfections in hardware and operating environments. Everything required to build a linear analog amplifier relies on staying perfectly balanced in that central active region. But if we intentionally abandon that balance, the transistor serves an entirely different function. By flooding the base with excessive current, we overdrive the device past the active region and deep into saturation. The voltage drop across the component collapses, and it behaves like a closed switch, representing a digital logic 1. By cutting the base current to 0, we force the device into cutoff. The silicon stops conducting entirely, mimicking a fully open switch, a digital logic 0. In digital mode, the active region still exists, but it's traversed so quickly as voltage snaps between extremes that its analog properties become completely irrelevant. The same physical layers and mathematical curves that allow a transistor to delicately amplify an analog signal are also used to snap a circuit open and closed, forming the binary foundation of
For part 2 of this video, comment part 2 in comments. Thank you for watching. Keep growing every day with just a bit of knowledge. Like and subscribe for more content and continuous learning.